Okay, so it's just a trig review. Might do might do another one later, depending on how much we get through. But to start, I'll just talk about things I'll assume that we know. So, for instance, the Pythagorean theorem. So the Pythagorean theorem is in a right triangle with sides A, B, and a hypotenuse C. So for right triangles, hypotenuse C and legs A and B, that we have the relationship of the sides that A squared plus B squared is equal to C squared. So I won't prove that. The other thing that we'll assume is that that sides of similar triangles are proportional. So first of all, what does similar triangles mean? That's two triangles are similar. Two triangles are similar if they have equal angles. So what does it mean for the sides to be proportional? Is that if you have two triangles, maybe let's say these sides are parallel, that means that this side is equal to this side, or this angle is equal to that angle. You have a shared angle here, and this angle is equal to this angle. The sides are proportional. Like, so this is A, B, C, and this is, let's say, D, E, and F. That, for instance, A divided by D, so A is the side of the smaller triangle and D is the similar side of the larger triangle, is equal to B over E. So B is the vertical one and E is the vertical one, is equal to C over F. Right, so these are the sides of one triangle, and these are the sides of the other triangle. And that's only true if they're similar. Okay, and then another thing we'll say is that in triangles, larger sides are opposite larger angles. Okay, what does that mean? Is that if I have a triangle like this, and let's say this is angle A, this is angle B, this is angle C, and then maybe this is side little b, side little a, side little c. Let's use a different letter. C looks similar. Let's say this is D, little d. That if angle A is less than angle B is less than angle C, then side A is less than side B is less than side C. So, so if you just came in, I'm going to assume these things, and if more things pop up that we'll need to assume, I'll let you know. So with the Pythagorean theorem, that in right triangles, the hypotenuse squared is equal to the sum of the legs squared. That in similar triangles, sides are proportional, and larger sides are opposite larger angles in triangles. Actually, I'll even go about this in particular. Equilateral triangles have equal angles. So equilateral means all the sides are the same length. And isosceles triangles have two equal angles and sides. Okay. I guess maybe just to say that the angles in any triangle add up to 180 degrees or 2 pi radians. Okay, so let's start with that. And again, if more things come up, I'll talk about them. So the first thing with trigonometry is to talk about the circle. Okay, so the circle is defined by.
What?
Is that a question?
No, it's like a, I guess, extra study session run by my professor.
I see. What
I
song
think
is that?
someone's not. Make sure you're muted.
You know the one?
Oh,
Okay. I'm just muted everybody. If you want to ask a question, type it then. So circles are defined by a center and a radius. So points in the circle are points radius away from the center. So if you have the center here, x, y, and this is your radius, that all points away from the radius are on the circle. All right, so with this definition, we can actually come up with the definition of the equation of a circle. Just that. Hold on. Try that again. Okay, so if we position a circle with center at the origin, and with some radius, so if the radius is r, then this point would be r comma 0. This point would be 0 comma r. This point would be negative r comma 0. And this point would be 0 comma negative r. That if we what we can do is, if we draw a line, a straight line from the center to the edge of the circle, we know the length of this line is r. And if we draw a perpendicular, so a vertical line, that we can construct a right triangle. So so this point here, whatever this point is on the plane xy, it explicitly means that this point is x away from the center in the horizontal direction, and y direction and y up. So this is true for every single point on the circle. So this point here, let's call it like x1, y1. This also has the same relationship. The hypotenuse will always be r. The height of the triangle will always be whatever the y value is of the coordinate, and the length will always be at least the length of the absolute value of the x coordinate, but we'll just call that negative. So if this is true for every single point on the circle, then we have an explicit formula, right? How do you know if the point x, y is on the circle? So we see that every point on the circle has the same property. So the answer, if it satisfies the Pythagorean theorem. So for every single point, you can always draw a triangle, a right triangle, and we know by Pythagorean theorem that x squared plus y squared is equal to r squared. Now, there's only 4 points where you can't draw a triangle, right? This point, this point, this point, and this point, but these still satisfy, right? For example, here for r0, we have r squared plus 0 squared is equal to r squared, so that checks out. So for every point xy, this works. Okay. So that's the equation of a circle, and we can figure it out just based on triangles. Okay. So that's just circles in general. Oh dear. Okay, there we go. So now let's look at the unit circle in particular. So why do we care about the unit circle? The unit circle is the circle centered at the origin with radius 1. So why do we care about that? Is, well, the origin is nice to work with because it's 0, 0. Radius 1 is nice to work with because it's 1. And 1 is an easy number to work with. Okay. Okay, so let's draw the unit circle. So this is radius 1. And we have some x and y. So all these right triangles will always satisfy x squared plus y squared is equal to 1 squared. Okay, so speaking of the unit circle, let's think about another way to describe points in the circle. Okay, so points obviously can be described as an x and a y value, right? We can think of it as x and y. It's some distance x away from the center and some height away. That's how we can describe it. However, circles are nice. And so, because if you draw a ray, so remember a ray is like a half open line. Starting at the origin, at some angle, from the x-axis. Okay, so I'm gonna start my ray at the origin, and I'm going to draw a ray at some angle from the x-axis. So notice that the ray only hits the circle once, right? So the ray intersects the circle at one point. So why is this nice? Essentially, instead of describing points in the circle as x direction and y direction, every angle corresponds to a point on the circle. So if you give me an angle, I can tell you a point on the circle. So if this is my angle here, then I know what point on the circle you're talking about. This one up here, x, y. So our goal is, how can we identify x and y by the angle theta? So something that we do know is that as theta changes, the x and the y are changing as well. So as theta maybe is increasing, what is happening to the x and the y? Maybe the x is decreasing, but the y's are increasing, for instance. Right? For instance, let's look at, so if this is the theta here, and then let's look at maybe a theta over here, that the new x and y, the x is going to be shorter and the y is going to be bigger. So, but what is always going to be true? X and y always satisfy x squared plus y squared is equal to 1. So this is the idea. So since as theta changes, x and y are changing as well, well, let's make a function such that you plug in in theta and get x back. Let's make a function so that when you plug in theta and you get the y value back. If you can figure out a function that does this, then we can exactly say, if I know what theta is, I know what x and y are. So that's precisely what sine and cosine are. So let cosine be the function that when you plug in theta, it outputs the x coordinate on the unit circle. So here is the unit circle. I have some ray that hits the circle at some point, and this ray has some angle to the x-axis. So I'm defining cosine as just let it be the thing that tells me what the x value is. So this will be called cosine of the angle. So cosine will tell me what the x value is for that angle. And similarly, we're going to let sine, so be the function such that when you plug in theta, it outputs the y coordinate. So you give me an angle. So this is how we're defining cosine for everything. So from now on, we're making up this function, right? So the idea is I have a nice way to talk about points in the circle just by saying angle. Give me angle, I can tell you what point is on the circle. So we're making up these functions called sine and cosine that say, that will describe for you what the x and y values are for the angle. So that's, so we're making this up. We're making up this function. Does that make sense? So we can see that angle will always give you point on circle. And now we're trying to find a relationship between angle and point. So this is an explicit relationship. The x value is called cosine of the angle, and the y value is called sine of the angle. So we haven't even talked about how to calculate these things yet, but just that this will be the relationship. It's some function, obviously, right? As theta changes, sine and cosine are changing. And it's a function, right? For the same angle, I don't get two x values back, right? For the same angle, I don't get two y values back, etc. So, so given that, now we'll talk about maybe how to find some exact values of sine and cosine. So there are four values we know explicitly. So if this is the unit circle, this point is 1, 0. This point is 0, 1. This point is -1, 0. And this point is 0, -1. So if we define sine of theta is equal to the y coordinate, of the intersection of circle and ray with angle theta, then let's take the ray with angle 0. This is the ray with angle 0. Of course, when I'm talking about angle, I'm talking about angle to the x-axis. So that tells me explicitly that these values will tell me what sine and cosine are for angle 0. So 1 is the x value, so that must be cosine of 0. This is how we define what sine and cosine are. So 0 must be sine of 0. Does that make sense? I'm purely just making up these functions called sine and cosine. I could have called them anything else, but convention says let's just call them sine and cosine. So now let's take the ray with angle 90 degrees, or pi over 2. So because we know what the point is, we'll call cosine of 90 equal to, what's the x value? 0. And sine of 90 is equal to the y value, which is 1. Now let's take a ray that makes an angle of 180. So this is also pi over 2, and this is pi. So we can just look at the point here. That means that cosine of pi is -1. It's -1, and sine of pi is 0. So now let's take the ray that is 180 plus 90, or 270. This one here. It's 270, or 3 pi over 2. And why is it 3 pi over 2? Well, it's just pi plus pi over 2. And again, why is it pi? It's just pi over 2 plus pi over 2. So this tells us that cosine of 270 is equal to 0, because I'm looking at the x value. And sine of 270 is equal to the y value of -1. And again, I look at the ray with angle 360, and I'm back to 0. All right, does that make sense for those values? Yeah, I mean, there are study sheets out there with these values. It's pretty easy to find. What I'm doing here is just kind of explaining where it all comes from. Yeah, cosine of pi is -1. Well, it's because of how we defined it, right? It's the x value of the intersection point between the circle and the ray. So it's not, I mean, you know about degrees and radians? Okay, so degrees versus radians. So it's just a different way to measure angles. So you could measure angles by 360 degrees in a circle, or you could measure angles a different way using yes, this number called pi, which is directly correspondent to like the ratio between the diameter and the circumference. You could measure it by a full circle makes 2 pi. So 360 degrees is equal to 2 pi radians. So yes, pi is 3.14, but again, it's a relationship between the circumference and the diameter. Right? There's not, it's not saying that 360 is equal to the number 2 pi. It's just a different way of measuring angle. Does that make sense? Yeah. Okay. So the way you kind of go from angle to pi is if you take a degree I can't erase today. You take a degree and you multiply it by pi over 180, you get the same thing in radians. So that's how you go from degree to radians. So for instance, if you take 360 and multiply by pi over 180, you get 2 pi back. Okay, so let's think about other calculations. For sine and cosine. So, and remember, sine and cosine is just the x and y value for a ray intersecting the unit circle. So let's think about an equilateral triangle. With length 1. So if every equilateral triangle means the sides are the same, remember last time or earlier we said that the angles must be equal. So if there are 180 degrees in a triangle, and all the angles must be the same, that means that every angle must be 60 degrees. So every angle, 60 degrees. So all we need to do now is we'll figure out if this is the circle, if we want to make a circle, or this is the center, we would want to find out what this x and y value is. We can actually do this in a couple ways. One way we could do is we can start with a right triangle with angle 60. So let's have a right triangle with angle 60, and let's let the hypotenuse be length 1. So we want to find out what the size of this triangle is. So if this angle is 60 and this angle is 90, that's 60 plus 90 plus something is equal to 180. If you do that, you find that x is equal to 30. So now what we can do is make a copy. copy of the triangle on the other side. Essentially what I'm going to do is going to like reflect this triangle about this line. So if I reflect it, all the angles are the same, right? I have the right angle, I have 60, and I have 30, and I have length 1. Does that make sense? I'm just reflecting that triangle on the vertical. So what happens is I get it if I look at the big triangle as a whole, where I ignore that middle part, then I actually get an equilateral triangle that we had in the beginning. So this is length 1, this is length 1, and this whole thing is length 1. So what happens? What does that tell us immediately? Well, that tells us that this side must have been 1/2. There's no other choice, right? And why is that? It's because, well, if I'm reflecting this triangle, that this side must equal this side. So I'm just reflecting it, right? I'm not changing that length. So since I know that all the sides of the big triangle must be 1, then the half of it must have been half of 1. Is that clear? There's only one choice for the side, that side length. So we can use the Pythagorean theorem to figure out the other side. So this is 1. We figured out this is 1/2 because when you flip it, you get an equilateral triangle. So we can figure out this side here by using the Pythagorean theorem. So 1/2 squared plus x squared is equal to 1 squared. Right, so that means that 1/4 is equal to x plus x squared is equal to 1. So x squared is equal to 3/4. So x is equal to radical 3/2. This must be radical 3/2. Does that make sense? And again, why is that true? It's because when we reflected it, you get an equilateral triangle. Okay, so this is always true, right? Whenever I have a triangle with length 1, with hypotenuse 1, and an angle 60, that these must be the other lengths of the triangle. And of course, this angle 30 because we figured it out earlier. So, we might call this the 30, 60, 90 triangle. So length 1/2 will always be opposite 30. Length radical 3/2 is always opposite 60. And then obviously, because we designed it this way, hypotenuse is 1. So one thing to remember is opposite sides, larger angles are opposite larger sides. So this also tells you a relationship between these values. So if you don't know what radical 3 is, well, it's obviously bigger than 1/2 because for a couple of reasons, right? Radical 3 is bigger than 1. But this could help you kind of remember the values. If you just remember that property that opposite larger angles are opposite larger sides. Okay, so let's go back to our circle now. So let's have a ray with angle 60. So when it hits the triangle, and sorry, when it hits the circle and then we drop down a perpendicular, we get a triangle, a right triangle. So since this is 90, this is 60, this must be 30. So we just showed that for a 30, 60, 90 triangle, we just proved that, well, this side must be 1/2, it's the side opposite 30, and this side must be radical 3/2. So this automatically tells you what sine and cosine of those angles are, right? So that means that cosine of 60, okay, cosine of 60 must be 1/2. Sine of 60 must equal radical 3/2. Does that make sense? And again, if you want that in radian form, cosine of pi/3 is 1/2, and cosine or sine of pi/3 is radical 3/2. Okay, is that clear? Okay, so let's do 30. degrees. So I have a point here, it's a circle, and I drop down a perpendicular. And well, if this is 30 and this is pi/2, or this is 90, this must be 60. So again, I have hypotenuse 1. And but we know what the sides of these the sides of this triangle is, right? This is also 30, 60, 90. So this length must be radical 3/2. And this height must be 1/2. Okay, so someone tell me what cosine of 30 is. It's just the x value, which must be radical 3/2. Yep. So sine of 30 must be 1/2. So cosine of pi/6 must be radical 3/2. And sine of pi/6 is equal to 1/2. All right. Is it making a bit more sense? Okay, great. Okay, let's do another nice angle. Let's think about isosceles triangles. So let's have a triangle, or let's have an isosceles right triangle. So if I have a right angle, and let's call this length 1, and let's suppose these angles are the same. So we know exactly what those angles are because 90 plus 2x is equal to 180. So when you find x, it's 45. Or pi/4 if you like radians. So this is pi/4. This is pi/4. And we could also figure out what the side lengths are because it's isosceles, right? This length must equal this length because equal angles are opposite equal sides. So by Pythagorean theorem, if this is a or something, we have a squared plus a squared is equal to 1, or 2a squared is equal to 1. A squared is equal to 1/2. So a is equal to 1 over radical 2. Or if we want to rationalize it, it's radical 2 over 2. So these sides must equal radical 2 over 2. That makes sense? So let's use this in a circle. So here's a ray with angle 45. And at this point, let's drop down a perpendicular. If this angle is 45, this angle must also be 45 since this is a triangle, a right triangle. And if this is length 1, and we just figured out what the sides of this must be. This must be radical 2 over 2. And this must equal radical 2 over 2. So this tells us exactly what cosine of 45 must be radical 2 over 2. And sine of 45 must equal radical 2 over 2. Cosine of pi over 4 must equal radical 2 over 2. And sine of pi over 4 must equal radical 2 over 2. All right. Questions about that? Okay, so now let's do something else. So you may remember about like SOHCAHTOA, right? If that's something you may have learned. So we haven't talked about tangent yet, but there's a reason for this and we can figure it out. So let's make a right triangle. And let's have this be an angle. And let's let this be let's let this be O for opposite. Let this be A for adjacent. Let this be H for hypotenuse. So right now we have no idea what sine of theta is because we only know the sine of theta is only defined for right triangles with hypotenuse 1. So what can we do to make this a triangle with hypotenuse 1? So what we can do is we can make similar triangles. Make a similar triangle that has hypotenuse 1. Now, how do you do that? Well, we know how to make, we know what similar triangles mean, right? Similar triangles mean that sides are proportional. So in essence, if I want to make this, if I turn this hypotenuse into 1, then I must scale down the other sides accordingly. So how do you do that? If I have side H, side O, and side A, and I want to scale this down to 1, essentially what you're doing is you're dividing the length of the hypotenuse by itself. So I'm taking the hypotenuse and dividing it by itself, which is 1. So I must do the same thing to the other sides, right? Because I want to maintain the proportional. I want to make sure if I want a similar triangle, these sides need to be proportional. So I'll take the opposite side and divide it by the length of the hypotenuse, because I want it to be proportional again. and I'll take the adjacent side and divide it by the hypotenuse. So since I'm scaling back every side of the triangle proportionally, these two triangles will be similar. So now we have a right triangle with hypotenuse 1. Since it has hypotenuse 1, this must be somewhere on the unit circle. And we know what these lengths are. It's whatever A over H is, and it's whatever O over H is with some angle. So what is sine of, let's do sine of the angle.
O over H?
Yeah, over H. And what is cosine? A over H. Cool, so that tells you that, so this angle is the same angle in all of these cases, great, because this is, these are similar triangles. So it must be true in this original triangle. So sine of the angle is the opposite side divided by the hypotenuse, because that's what it is in this case. And that cosine of the angle is adjacent over the hypotenuse. And again, it's because we're bringing it back to a unit circle. The definition of sine is not opposite over hypotenuse. It's coming from the unit circle. So now, because of similar triangles, we can generalize sine and cosine to all triangles, not just the unit circle. But it's because we develop it from the unit circle, and because similar triangles are a thing, we've expanded it to all triangles. All right. Does that make sense? Any questions on that? Okay. I guess maybe what I can do is, let's talk about maybe tangent and those other ones. So sine and cosine are really the only ones you really need to think about, because every other trig function is some relationship with sine and cosine. So tangent we'll define as sine divided by cosine. So think of it as just a shorthand way of saying sine divided by cosine. We'll define secant as 1 divided by cosine. We'll define cosecant as 1 divided by sine. And we'll say cotangent is 1 over tangent, or cosine over sine. So those are just things you should memorize. But again, sine and cosine are the main players here. I guess one last thing before we go, I'll stop at like 5, are the Pythagorean identities. So remember the unit circle had the equation of x squared plus y squared is equal to 1, right? That came from the Pythagorean theorem. And we know that xy on the unit circle corresponds directly from cos theta and sine theta. So this tells you that if you plug in x and y for cosine and sine, you get cosine of theta squared plus sine of theta squared is equal to 1. Or another way of saying this, instead of putting the 2 out there, sometimes we just put the 2 right in front of the cosine. So that's why that cosine squared plus sine squared is equal to 1. And again, that's just because how we defined sine and cosine to begin with. So now what we can do is we can come up with some other identities by fiddling around with this equation. So why don't we divide everything by cosine squared? So I'm going to take every single term in here and divide it by cosine squared. So so this becomes 1, right? If I divide cosine squared by cosine squared, I get 1. If I divide sine squared divided by cosine squared, I get tangent. If I divide 1 by cosine, I get secant. That's how we defined what secant was. So that gives you a formula, a new Pythagorean formula. Now we do the same thing, but divide everything by sine. So cosine divided by sine, that's cotangent. Sine divided by sine is 1. And 1 divided by sine is cosecant. So just by fiddling, again, this was just from this original function, or this original equation, cosine squared plus sine squared equals 1. We can develop other relationships between the other trigonometric functions. And if you like, and you can do the same thing by solving for each of these things. But yeah, those are other identities that we have for sine and cosine. Oh, yeah. So tangent is equal to sine over cosine. But it turns out that it's also equal to, like, this value. The value of tangent, right? The value of cosine is this value, right? Or of that side is cosine. The value of this is sine. And actually don't know the proof. Look at that. But so if I take that same ray and I extend it through and draw a vertical line at x equals 1, that where it hits this vertical line, the height is actually tangent. That's why I draw that, because it is that. So if you take sine divided by cosine, you'll always get this this value up here. Actually, I think we know. Yeah, we should know why that's true, right? Here, let's figure it out. Because of similar triangles. These triangles are similar, right? This is a right angle. This is a right angle. This is angle, whatever that is, and this is equal to this angle because of parallel lines. So if this side is sine of theta, and this side is cosine of theta, and this length is 1, and we don't know what this length is, let's say, that by proportionality, cosine of theta divided by 1 is equal to sine theta divided by x. So x is equal to sine over cosine. Okay, actually I like that better. So we call tangent theta equal to sine over cosine. So this is actually a nicer definition of tangent. So the definition of tangent is not sine over cosine. It's just this length, which happens to be sine over cosine. We just showed it there by similar triangles. Yes, 1 over sine is equal to cosecant. It's a little weird with the S and the C not matching up. Okay, I think I'll probably be finished there. I mean, unless you have questions right now, I can answer them. I figured maybe if we do this another time, maybe I'll go through all of the angles in the unit circle. We haven't really, I guess, there's not much really to do after that. I could even show you. So today we did 30 degrees, we did 45 degrees, and we did 60 degrees. And you can just kind of mirror these on every single, everywhere. So like if you make a 30, 60, 90 triangle over here, well, you can figure out what this angle is, right? This angle would be 180 minus 30. So now you know what that value is. So yeah, maybe if we do it again, I'll kind of carefully go through everything. And I guess other things would be like some of the formulas, like the double angle and stuff like that. You can go through that. Oh yeah, of course. I feel like trig is always a big hurdle for people. So I mean, it's helpful for me too. So we don't have to spend so much time in class on it. But yeah, I hope it's helpful. But yeah, I guess if there are any other questions, or else I'll stop recording. Yeah, I'll stop recording.